equation and combine those logs. That will be our first step. So we'll rewrite this as log base 3 of x plus log base 3 of x plus 2 equals 1. And then what log property do we use to combine two logs that are being added? How do we combine those two logs? Okay, rule. What was that?
This is the product.
Yep, log of a product. That's right. Right there. And then the variable is trapped inside the log, so somehow we have to get that out. And so here's where we convert. We always think anytime we have a log equation, we convert it to an exponential, and vice versa. Anytime we have an exponential, we could convert it to a log. Kind of depends on what we're trying to do. So here, if we change to an exponential, we use that spiral idea. The inside of the log is equal to the base of the log raised to the other side. You get that? And so it's 3 to the 1. Doesn't look very exponential here, but 3 to the 1 is, we're getting rid of the log by going to an exponential form, but we can simplify that exponential piece, 3 to the 1. So that gives us x squared plus 2x minus 3 is equal to 0. Nonlinear equation, everything to one side and factor. That's always our procedure for a nonlinear equation. And then we hope we can factor. It looks like a plus 3 and a minus 1. That works. So that tells us that our potential solutions are negative 3 and 1. And then what's the last step? We have to check. We have to check and make sure that we're not taking the log of a number that's equal to or less than 0. And are we? If we plug in negative 3, are those okay? Not okay, right? But if we plug in 1, it's okay. So we just have to check and make sure that if that number causes the inside of log to be 0 or negative, then it's out. So our only solution here is x is equal to 1. That's our only one. Does that make sense? No? No sense at all?
No.
None?
How do we check it again?
We take the x value and we plug it back in up here.
Right.
So we look at both of the log arguments up here. And what's inside a log cannot be less than or equal to 0. We know that a log function has this graph, where the y-axis is an asymptote. So we cannot put x values into a log function that are less than or equal to 0.
Okay.
So the check is simply, does that x value cause the inside of any of the logs to be less than or equal to 0? If we plug in negative 3 here, then we're taking log base 3 of negative 3, which is not allowed. If we plug in negative 3 here, we're taking log base 3 of negative 1, which is not allowed.
Okay.
Does that make sense?
Yeah, that makes sense.
Perfect sense?
Yeah.
Excellent. That's our goal. Perfect sense. Okay, that crazy looking thing. Here we have an exponential, and just like a few minutes ago I said, sometimes you have an exponential, you want to flip it over to a log because it'll make it easier to solve. And here, our problem is that the variable is in the exponent position, so we can't easily solve for the x. We could easily solve for the x if the variable is up there, if we have something like this. If we were able to equate the bases like that, then no problem. Then we can go without taking a log of both sides. Here you can just equate the exponents and you're good to go. You could say that the exponent on the left is equal to the exponent on the right, solve for x. Can't do that here, so what do we do to both sides of the equation? Our favorite operation, take the natural log of both sides. And on the left side, the x minus 5 will come down in front as a multiplier. Make sure that you can actually not do this one. I'm going to do this one one step at a time on the right. The right's a little more complicated. Make sure that when you bring down this exponent, it's in parentheses. Right? This entire exponent is coming in front. It's very common to forget your parentheses, and then the natural log of 4 is not being distributed properly to the x. So make sure that entire exponent is wrapped up in parentheses. All right. Now on the right, it's a little more complicated. We have let's distribute this on the left. And then on the right, we have to use a log property. Our predominant operation in here is multiplication. So we don't bring the x down in front because the power is not the predominant. It's not the first operation that's happening. That's the predominant operation that we have to deal with first. So how do we bust this apart? So we break it apart with addition. So that's going to be the natural log of 121 plus the natural log of 3 raised to the x power. Now the x can come down over there on the right. And I'm going to move this constant term here. These constants all should go to the right. And this guy over here is going to come to the left with the x in it. So the x is coming down, and then I'm going to subtract it over to the left. So that will be x natural log of 3. On the right, we have natural log of 121 plus 5 times the natural log of 4. And then how do we isolate x? Right now, x is in 2 places. Factor it. So on the left, we factor out the x. And on the right, there is some stuff you can do. On the test, unless you're asked to combine all the logs into one, I don't care if you leave it how it is. If you're asked to combine it, though, how would that 5 come into play? What would we do if the 5 is the one that ends up combining all these logs in the numerator? What would we do? Make it an exponent. So if we pop that up there as an exponent, we get 4 raised to the 5th power, which is what? Like 1024 or something? Let me type that in. Tell us. Yep. 1024? Thank you. Right, so that's that goes in there. And we could, again, only, oops, I shouldn't divide yet. I have to divide both sides, right? So if I'm going to do that, I should write it over here also, divided by natural log of 4. Okay, so our final step then, x is equal to, again, if you want to, you could make this natural log. If I don't ask for you to combine it into one, you don't have to. But if you wanted to, you could combine this into 1 log in the numerator, and you could combine this into 1 log in the denominator. Can you combine those 2 logs into a single log? Where you have log of A divided by log of B. Can you combine those further? No. Can't combine those. So that would be the exact answer. And depending on what the instructions are, if it says to type this into your calculator for an approximation, you would type that in. Okay. Did it ask for an approximation?
It did.
So anyone unsure how to enter that into your calculator? Make sure you wrap your log arguments. So you'll type into your calculator natural log this times that, close the parentheses, divided natural log of 4 divided by 3, close the parentheses. And what do we get when we type that in for a couple decimals? Any ideas? 40.76. Confirmation from someone? Yeah. All right, cool. 40.76 is 40.76. Any questions on why or how? All right, so those are two really good questions. A final exam in precalculus is pretty hard to imagine not having an exponential equation and a log equation. Those are both very representative types of problems that you could see in a final. So, great question. Any other from the homework or the quiz that you want to cover? All right, let's go. We just got a couple here from before break. We'll do a couple of these, and then we'll start doing some more graphing of conics. When you look at that, we know it's going to be a conic. We've got an x squared, we have an x, we have a y squared and a y, but we don't know for sure which it is yet. You can probably safely assume it's not a parabola, because we have an x squared and a y squared. It looks like it's probably going to be an ellipse because we have that plus there. But sometimes when you complete the square, it might turn into something you're not quite expecting. This one doesn't have any big surprises. So when we want to put this in standard conic form, we have to group the x's and group the y's. Now we'll write the x group in descending form, the y group in descending order. We'll put the constant on the right. For completing the square. And when we complete the square, we know that magical little formula, divide by 2 and square. But we can't divide by 2 and square until we've done something first. Before we can do the divide by 2 and square piece, what do we have to do? Factor. Factor first. And by factor, what we mean is factor 5 out of the x group. We factor out the leading coefficient out of the x group. We factor the leading coefficient, bless you, out of the y group. So that's our first step. We're going to factor out those leading coefficients. And then we're in a position to do the divide by 2 and square. So with the x group, what are we adding into the blank here? 9. So we take the coefficient of x, divide it by 2, and then square it. So 6 divided by 2 is 3, 3 squared is 9. And what about for the y term here? Divide by 2 and square, we get a 1. We've just added stuff to the left. In order to keep the balance, we have to add the same stuff to the right. The one trick that we have to be very careful, it's not a trick, but the one issue is that when we add 9 inside parentheses, we have to take the multiplier in front into consideration. If we were to distribute this 5 back across, we would not have 5x squared plus 30x plus 9. We'd have 5x squared plus 30x plus 45. So adding the 9 inside is really adding 45 to the left. So if we've added 45 to the left, we have to balance that out by adding 45 to the right-hand side also. So not just 9. Similarly, with the 1 that we added, we didn't really add just 1 to the left. If you distribute the 64 back, you realize, oh, we really added 64. So on the right-hand side, to keep the balance, we have to add 64. Keep the balance. Now we're in a position where we can factor. So this will always be, both of these will always be perfect square trinomials every single time. all those together, 320? All right? 320, yeah, okay, great. 109 plus 211, 320. Okay, not quite there. With the two conics, with the ellipse and the hyperbola, the right-hand side always has to be 1. So we're not quite there. We have to do some division. So we divide those sides by 320, which means divide every term by 320. And how many times does 5 go into 320? 64. And how many times does 64 go into 320? Let's do this. 5. So there is our standard form. So that's our standard form, and from that form we can identify the center of the ellipse. And why do I know it's an ellipse? Because it's a plus in the middle. If there was a minus, then it would be a hyperbola. And what is our center? Negative 3, negative 1. Exactly. We're okay with that? So for both the x and the y, it's opposite of what we see. And then, if we were to find the foci, we would have to use a Pythagorean theorem idea. And so this c is different than that c. This is a little c. And little c is going to measure the distance from the center of the ellipse out to a focus. And what is c squared equal to? What do we do with our denominators?
Is it 64 minus 5?
Bingo. That we subtract. We do the opposite of what the standard equation has in it. So for an ellipse, we subtract the denominators, but for a hyperbola, we will add the denominators. So c squared will be 64 minus 5, which is 59. So that tells us that c is the positive square root of 59. This little c is a distance. I'm going to make this c for center a little bigger, just to make sure it's not interpreted as the same c. So that little c, technically, if you take the square root, you get plus or minus. But in the context of this application, we know that c is defined to be a positive distance, so we don't need to put the minus somewhere. And didn't ask us to graph this, but if we wanted to graph it, we could graph it now. The center is negative 3, negative 1. There's our center right there. And then how far left and right do we go from the center? How far left and right? So to get to the vertices, so we would go left and right square root of 59 to get to the foci. Usually we'll do the foci after we get the vertices of the ellipse, though. So to get to the vertices, we would go left and right 8. So we look under the x's, take the square root, and that tells us how far in the x direction to go. We look under the y to figure out how far in the y direction to go. And then we look over there to figure out where the foci are. And the foci are always on the major axis, the longest axis. So our two major vertices that are way out here, and 1, 2, 3, 4, 5, 6, and right there. So those are our two major vertices. And then our minor vertices, square root of 5, that's between 2 and 3. So we just have to guesstimate it, just a little bit up there. Go down between 2 and 3, so about right there. So there's our the 4 points that are connected for the ellipse. There's something about like that. Then the foci are on the major axis. Major axis is the longer axis. And those foci, square root of 59, that's somewhere between 7 and 8. Square root of 49 is 7, square root of 64 is 8, so somewhere between 7 and 8. So we're pretty far over there. We're right in between the last two tick marks there. So there are our two foci. Focus 1, focus 2. And how about the coordinates for those foci? What's the y coordinate first? Those are easy. That's easy. Earth. -1 for both. And then how about the x coordinates for the foci? Yeah, exactly. So we start at the -3 as the x value in the center, and then we know from that x value in the center we're going to go positive 59 to the right, square root of 59 to the right, and minus square root of 59 to the left. So we'll do whatever that x value is, which is -3, and then plus or minus root 59. Yeah. Those will be the two foci. Okay, one other quick reminder. I reminded you this before, but this seems to be a confusing issue. The change of base formula, change of base can go to any base you want. When you look at most calculators, they don't have a base 3 or a base 5. Most only have common log, which is base 10, and natural log, which is base E. So you can switch to any base you want. The argument is always in the numerator, and the base is always in the denominator, and then you can choose whatever base you want all the way across. This, again, is the most common one to choose. But those ratios are all the same. Doesn't matter which base you pick. They all will give you 2.6801, etc. Okay, so let's go to some more hyperbola stuff. So we started the hyperbolas on Thursday before break, long ago, back in mid-November. It's not quite winter though, is it? We're not in winter yet, right? Still fall. Back in winter? No. In winter? Really? The good thing is calculators are indestructible. Okay, so I would write this stuff down. This is a summary that, as you're bored and you're looking to fall asleep at night, you could stare at all these letters and try to figure out exactly what they're saying. But I think it's just much easier in practice. And so we'll do a bunch of examples. If we look at this one, a couple of key features. If the x's are first, it opens horizontally. If the y's are first, it's going to open vertically. And you can remember that by looking at the most basic type of hyperbola. If you looked at the most basic hyperbola, would just be something like x squared minus y squared equals 1, or y squared minus x squared equals 1. So if we look at the most basic hyperbolas centered at the origin, no crazy denominators, it should be, I went through this last week, or 2 weeks ago, but it's probably a good idea to go through it again since some of you have filled your bodies with so many calories that you squeezed out math knowledge. So these basic hyperbolas give us the sense of why they open either horizontally or vertically. And like with the ellipses, we look for intercepts. So for this guy, I would say to myself, what are the x-intercepts? And to find the x-intercepts, what do we plug in for y?
0.
0. And so then we have x squared equals 1, so we get x is equal to plus or minus 1. What about y-intercepts? Does it have y-intercepts? What would you plug in to see the y-intercepts?
0 for
x, 0 for x, and then what do you get? You get y squared equals -1. Y squared equals -1, no solution in the real numbers. So this one has x-intercepts and no y-intercepts. And you can put like a invisible dot here that's not going to be part of the graph if you want, because that will allow us to build what is usually referred to as the fundamental rectangle right there. But these points here are on the graph. It has x-intercepts. It does not have y-intercepts. Those y values that we pick there are just to build that fundamental rectangle, which is a guide. And that fundamental rectangle is then used to complete the graph by putting in asymptotes. And then the graph of this hyperbola has to go through the x-intercepts, and it would look something like that. So that's why in our head, when we're looking at a hyperbola that's then more complicated and shifted, we think, okay, if the x's are first, it's got to have x-intercepts if it wasn't shifted. So x-intercepts when it's not shifted means it's opening horizontally. So then when we look at a more complicated one that's got all these shifts, if the x's are first, it's still going to open horizontally if the x's are first. And then what would, just out of for grins, the asymptotes here would be y equals what? X and negative x, right? There's always 2, so we always have to take that slope and put a plus or minus in front. So those would be the asymptotes. And let's go ahead and complete this by finding the foci. So the foci, we have to use little c, and we say c squared is equal to, with the hyperbola, we can imagine these denominators here of 1. So what do we do with the denominators for the hyperbola? We add them. We just do the opposite of what the standard equation is. So if we add the denominators, we'll get c squared. So we get that c will be the positive square root of 2. So then from the center, we're going to go between 1 unit and 2 units to the right and left. So there will be our foci. Foci F1 and F2 right there. And the coordinates of those foci, the y value is certainly 0. And because we're centered at the origin, we're just going plus or minus root 2. Those will be the foci. All right, this one over here is super similar. But here, if we let x be 0, we get y is equal to plus or minus 1. So we definitely have y-intercepts. But the x-intercepts are non-existent, but we still sort of look below the x's and say, oh, we're going to go up and down, or right and left 1 unit from the center to build this fundamental rectangle. We're not saying that there are x-intercepts. We're saying that those 2 x values are going to be used to build the rectangle. So this axis, there's 2 axes here. This axis is called the transverse axis, the one that connects the arches. And then this other one is usually referred to as the conjugate axis. And so we're just by figuring out where the endpoints of the conjugate axis is. So over here, same process. We draw the diagonals through this unit square. And the only difference is that this time our hyperbola is opening up and down. So I would say that's vertically opening instead of horizontally opening. Asymptotes will be the same. The foci will be almost the same. Instead of being horizontal, they'll be vertical though. So the foci will be something like that. Okay, so we just use these basic ones to get a better sense of, okay, x is first, horizontal, y is first, vertical. That's helpful to orient yourself. And so when you're looking at this, you're not getting super tangled up in all these letters. Now, the one other piece I do want to point out the asymptotes, if we have a shifted situation, it's totally fine to write your asymptotes as shifted lines and not simplify them and write them in mx plus b form. All we do here, instead of y equals slope times x, we put y minus k on the left, and we put x minus h on the right. And just leave it like that. Don't be any more complicated. And notice that the slope is always, slope is always change in y over change in x. So we look under the y's to get the numerator, we look under the x's to get the denominator. Same down here, when we look at the slope for the asymptotes, we look under the y's, which is we're in A now, that's the numerator, under the y's, that's rise, under the x's, that's run. It's always y over x. Okay, so let's do a few of these. Let's start with this shifted one. And everything is based on the center. Once you know the center, you're kind of running away from the center, horizontally or vertically. And what would our center be for this one? 5, -2. That's our center. And that's where we start. We're going to go to 5, -2. That's our center. Right there. And then we're going to go horizontally and vertically from that center. So how far horizontally are we going to move from the center? 4. So to figure out how far horizontally to move, we look under the x's and take the square root. So under the x's we have 4 squared, so that means we're going to go 4 to the right and 4 to the left. And then how far vertically? 3. We look under the y's, take the square root, and that's going to be our indicator as to how to get to the minor vertices. The vertices that are on the minor axis. So there is, and then we can graph it, so there's our ellipse. And the foci are always going to be on the major axis. The major axis in this case is horizontal. The major axis is just the longer axis. The minor axis is the shorter one. And the foci are always on the major axis. So to find the foci, we need to use little c. So little c squared will be summary difference of the denominators. Oh, what the heck did I just do? I drew an ellipse. Is that the equation of an ellipse? No. If this was a plus, then that would be a graph. But it's a minus. So it's not an ellipse. What is it? Yeah, hyperbola. So instead of drawing the ellipse, what do we draw instead? The box. We draw the fundamental rectangle right there. Fundamental rectangle. Okay. So to get to the foci, c squared will be summary difference. Sum, we add the denominators, so that tells us c is equal to 5. And let's draw our diagonals through the fundamental rectangle. Those are our guides for the graph. Right through the corners. Okay, so should this one open horizontally or should this one open vertically?
Horizontally.
Well, x's are first, so horizontally. Exactly. So we go through those vertices and we approach both asymptotes. Through that vertex and approach both asymptotes. And then the foci will be 5 units from the center into these arches. So 1, 2, 3, 4, 5 is exactly 1 unit in. And then right there. So those will be the 2 foci. And you're generally going to be asked for the coordinates of the foci. And the y-coordinate for the foci will remain the same as the y-coordinate for the center. So that's -2. And then how about the x-coordinates? If you start at 5, you're going to add and subtract 5. And in this case, unlike the other case, we can simplify this because there's no square root. So we can simplify pretty easily there. And then the asymptotes, which a lot of folks find the most complicated, I think these are the most complicated part. But I don't think so. Right, so instead of y equals mx, we're going to do y plus 2 is equal to, let's see, what are the slopes of those lines going to be? Plus or minus up 3 over 4. Not 16 over 9, but the square root of 16 over the square root of 9. Right, so it's going to be, the rise is going to be 3 and the run is going to be 4. So 3/4. You can also look at your fundamental rectangle. From the center, you go up 3 over 4 to get back onto that diagonal line. So 3/4. And not just x, because it's all shifted around, we have to put 10x minus 5. And that's how you leave your asymptotes. Don't isolate y and distribute, just leave it like that. That is what we want for the asymptotic version. Any question on any of the steps there? A little bit more to it than an ellipse. An ellipse, you're done real fast because you get those 4 points and you connect them to form the ellipse. But for a hyperbola, you have to draw the rectangle, the asymptotes, find the asymptotes. Good. Let's do another one. So this one is not in standard form yet. We have to divide both sides by 4. I'm going to just put a 1 under the x's just for rings. Okay, so now it's in standard form. So you guys go ahead and try to graph it. Question? Not for the center. The center is always going to be, yeah, it's going to be 0, 0 in this case. It's always the number, it's always the shift.
Oh, it's always the shift.
Yep, it's always the shift that you see there. So in this one, there's actually no shifting. So it will be centered at the origin. Confusion says, so origin is the center. Yep. All right. I see lots of good answers. And once you get the habit, the hang of these ones, you can fly through them really. So given that our center is the origin, we see that we need to go up and down 2 from the origin. And we get that by looking under the y's. Under the y's tells us how far to go vertically from the origin, from the center. And then we go left and right 1. And if this was a plus here, we'd be done. There's our ellipse. But it's not an ellipse. It's a hyperbola, so we draw our fundamental rectangle. Connect our diagonals. And then we have to just remember, does it open horizontally or does it open vertically? Yeah, it's going to open vertically because the y's are first. So if it, which I guess it's not shifted, so you can actually say to yourself, oh, the y-intercepts are plus or minus 2. Since the y's are first, it's going to open vertically. Connects, goes through the vertices and gets close to the asymptotes. And then foci, we add the denominators. So little c squared will be 4 plus 1. So c is root 5. And those foci are on the y-axis in this case, and between 2 and 3 from the origin. So between 2 and 3, so they're here and here roughly. Focus 1, focus 2, and the coordinates for those foci would be 0 plus or minus square root 5. And the last step, the equations for the asymptotes. So the asymptotes, y equals plus or minus 2x, right? Look under the y's to get the numerator, 2. Look under the x's to get the denominator, 1. 2 over 1. Any questions on any step there? All right. That one's, let's not do that one. That one's a little too easy. I want to, let's do another shifted one. So let's suppose we have this. All right, so go ahead and try that one. See lots of correct centers, that's good. One really common mistake is just to sort of go in order and say, oh, the center is negative 1, 3. But you have to remember that the x coordinate of the center comes from the x's, so 3, negative 1. Any questions on your fundamental rectangle? Under the y's, you have a 4, so you're going to go up 2 and down 2. Under the x's, you have a 25, so you're going to go right 5 and left 5. And does it open vertically or horizontally? Vertically, yes. Nice wide hyperbola. Both sides, you add or subtract the denominators. Add. All right, so the both sides, between 5 and 6 from the center, correct? They're pretty far down there. I'll just put them like this. So what would the coordinates of the both sides be? X coordinate's the easy one. 3, same as the center. And then, right, exactly. So we use that y value for the center, which is negative 1, and it's from there at negative 1 that we're going to go up and down root 29. Bless you. Then the asymptotes, y plus 1 equals plus or minus the slope, and then x minus 3. So we just grab that y shift, put it on the left, the x shift, put it on the right, plus or minus, and the slope is what? 2/5. It's y over x. So it's y over x first, so we have to look under the y's, but it's not the whole denominator, it's the square root of the denominator, square root of the denominator, so it's 2/5. Also look at your fundamental rectangle. To get from there to this corner, you're going up 2 over 5. So you can always look right at your fundamental rectangle also. So 2/5. Your asymptotes. Let's try this guy. So here they give us two pieces of information. They tell us what the vertices are, they tell us what the foci are, and we want to generate the equation for the hyperbola. So I think it's really helpful to draw a little sketch to get a sense of what's going on. I think it's the easiest way to sort of piece it together. So vertices 1 and -1. Foci 2 and -2 on the x-axis. So focus 1, focus 2, and definitely this hyperbola. We don't know the steepness yet, but it's opening horizontally. So we know that much. We know it's opening horizontally. We know the center is 0, 0. So it's opening horizontally, so that means I'm going to put x's first. And I know the center is the origin, so I can piece together this much so far. So any questions there? Is that clear why we conclude the center is at the origin? Right, the center of the hyperbola has to be dead square right in the middle of the foci or the vertices. Right, the middle of the vertices is the origin. Okay? So we know that that's the structure of our equation so far. Now, under the x's tells us how far left and right we're going to go from the center. So what has to be under the x's? 1. Right? The distance that we traveled was 1 unit, and if we square 1, we end up with 1. Now, this is our mystery right there. We don't know that. But we do know what c squared is equal to. Right? C squared is equal to what? Yes, it's equal to 1 plus question mark. Definitely, we could say that. And from the graph up here, it's also equal to 4, right? Because c is the distance from the center, which is right there, out to a focus, and that's 2 units. So it's 2 units from the center to a focus, which means c is 2, which means c squared is 4. And then now we can take that and solve for question mark. So that tells us that that denominator is 3. So that tells us our final equation must be that. There's the final equation. That make sense? Drawing the sketch helps you just sort of orient things and put things in place. From the sketch, we know that c is 2, so c squared is 4. From the sketch, we know that x's are coming first. And we know that the denominator is 1 under the x's. And it's the denominator under the y's that's our question. We don't know what that is. But we do know that the sum of the denominators has to be c squared, and c squared is 4. So that allows us to solve for the second denominator. Let's do one more, and then we'll take a break. All right, so here, again, a sketch is going to be really helpful. This one, we're given the asymptotes. We're told that the asymptotes are 5 fourths, so up 5 over 4, so kind of steep, more steep than shallow. So 5 fourths. We've got those two in there. And one vertex is at 0, 3. Plus either one. So 0, 3 right there. Where does the other vertex have to be? -3. 0, -3. 1, 2, 3. So we know that this hyperbola is opening vertically. Okay. We can now draw the fundamental rectangle. So the fundamental rectangle has to go through those two vertices And the asymptotes have to go through the corners of that fundamental rectangle. All right, so let's start piecing together the equation. The center is the origin, obviously. So what comes first, y's or x's? Y's. So we know this much so far. Okay, for sure that. Now, what should go under the y's? What was that? 9. The distance from the center vertically is 3 to a vertex. So we square that to get the 9. And now we have to do a little bit of algebra. We have to figure out how far we're going left and right from the center to get these end points of the so-called conjugate axis. The conjugate axis is this thing right there. Well, how would we find that x value? Yeah, we know plug in 3 for y. So this point right here has a y value of 3, so that y value on the asymptote has to have a y value of 3. And we want to identify what the x value is. So yeah, we'll just do a little algebra here. We'll plug in 3 for the y value. 5 4 is x, so x will equal 12 divided by 5. So that x value right there is 12 fifths. 12 fifths comma 0, and that one would be minus 12 fifths comma 0. Okay, so if that's the x value over there, what goes below the x's? (144 over 25). And if we wrote it in completed form, typically what we would see is this as our final form. That form right there is great because we can see under the x's that it's 12 fifths, so we have to go left and right. But having a complex fraction is not ideal, so they would actually write it like that. Good. It's like opening a Christmas present. It's so fun. All right, let's take a break. Take a pen. And we'll do some other math. I think no, don't distribute. Is that what you said?
I think, yeah.
Yeah, don't distribute. What we're going to do is kind of this thing backwards. So the easiest way to look at it would be to write this as 9/4 in the denominator. This one's definitely a little bit harder. I wouldn't put one, I don't think this hard on the test. And then we can identify the center easily. That's going to be 1 negative 3. And if we go ahead and just deal with c squared right now, we're going to add those two. So it's going to be 9/4 plus 16. And I'm going to write 16 as 64 fourths. So that gives us 73 fourths. So pretty messy. C is going to be the square root of 73 over 2. All right. Then, from the center, 1 negative 3. The center. How far? Let's go up and down first. How far up and down? How far up and down? So from the center, we go up and down 4. We look under the y's to figure out that vertical up and down. So we're going to go up and down 4. 1, 2, 3, 4. That's 3, so that would be 4. And then right and left, we're going to go, how far? 3 halves, exactly. So 1.5 to the right, 1.5 to the left, so about right there. And then 1.5 about right there. This will allow us to build our fundamental rectangle. So it's kind of like that. Oops. And then, does this open horizontally or vertically? What was that? Horizontally, because the x's are first. So let's get these guys to our diagonals. And since x's are first, yeah, a nice flat hyperbola. All right. The foci, let's see, what's that? 64, so 8. So between 4 and 5, roughly. So I'll just put little x's here and here. And those foci will have the same y coordinate as the center. So that y coordinate was -3. And how about the x coordinates? The center is at 1, -3, so we're going to do 1, yeah, plus or minus this irrational number. And then to do our asymptotes, we'll do y plus 3 equals plus or minus, leave a blank, and then x minus 1. And here we have to do the rise over the run. The rise is 4. The run is 3/2. So it's 4 divided by 3/2, which we would simplify to 8/3. That's our final form for the asymptotes. That makes sense? Definitely a little more complicated if you have that constant multiplier out in front. All right, let's roll forward to the, we've done enough of those. All right, let's go to the parabola. So the parabola you've dealt with a lot for the last couple of years. The big difference is that we're going to write our parabola differently in terms of the equation. We're going to write it in the so-called conic form instead of the standard form that you're used to. You all know that this is the equation of a parabola in standard form, with the vertex being at hk, and if a is positive, it opens up. If a is negative, it opens down. So this is a vertical parabola. And some of you may have done a parabola that opens sideways by solving for x and writing this a little differently. Some of you may have. Not everybody, probably. But we're not going to use this form here. We're going to use a conic form instead. And to generate that conic form, the first thing we want to do is just understand the basic definition of a parabola. You've never actually defined a parabola until you got the conic sections. You were just told the graph of a quadratic equation is a parabola. A parabola was never defined. So this is the definition, which you did see in 121 when you got the conics. So the definition of a parabola, there's these two mysterious quantities, the focus and the directrix, and the parabola is kind of sandwiched between them. So the parabola is the set of points that are equidistant from the two. So this point right here is not on the parabola because that distance and that distance are not the same. This point is on the parabola because that distance and that distance are the same. So the parabola is kind of squeezed in between this distance to the directrix and the distance to the focus. Those have to be equal for a point to be on the parabola. Okay, so it's this process that sort of squeezes the points between these two quantities, the focus and the directrix. Okay. So we will have parabolas that open vertically, parabolas that open horizontally, and the same is true over here. There's going to be this common distance from the focus to the point, and from the point to this directrix. Directrix is a line, focus is a point. The distance from the focus to the vertex will be called P. And that distance is the same distance from the vertex to the directrix. So P is there and P is there. Same over here. That distance is P, that distance is P. If P is positive, your parabola opens up or right. And hold on one second. And let me just think for a second. Can P be positive or negative? Do we say that P is negative? Let's go think for a second whether we allow P to be. Let's think quick. Yeah. So P can be positive or negative. So if P is positive, it opens up or right. If P is negative, it's going to open down or left. If P is negative, so P can be negative. So here is our standard equation if we're centered at the origin, if the vertex is at the origin. We're going to see this and this as our two standard equations if we're centered at the origin, if the vertex is at the origin. Now this is totally backwards from typical functional notation. Here, y is a function of x, but we're putting the dependent variable on the right. We're putting the y on the right. So this is really backwards from what you've ever done before. You've always written y equals something, right? So this is just a little weird. We call this the conic form, and it will work. You'll see how it works. You could always solve for y and use the way that you've always solved. You've always graphed parabolas. That would absolutely work. You could do that. But most books these days use this conic form once we get the conics. So let me show you how it works. So in your mind, you should be thinking, isolate the square variable. Isolate the square variable. Normally you think isolate y and put everything else on the right. Now we're going to isolate x squared or y squared. Okay, that's already isolated. Our standard form when we isolate x squared is 4py. Our standard form when we isolate y squared is y squared equals 4px. So those are our standard forms. And the whole idea is to solve for p. In order to find this mystery focus and this mystery directrix, you need to know p. So right away we know the vertex is 0, 0. And to solve for p, we simply equate 4p equal to that coefficient. We set those two equal, and that's how we solve for p. So p, in this case, will be 4. Same thing over here. We're going to set 4p equal to the coefficient. So here p will be negative 1/2. All right? So that part's pretty mechanical. Once you've isolated your square, you set 4p equal to the coefficient. So let's draw the graph then of these. This one has x squared y linear. So do you think this is going to open vertically or horizontally? Vertically. You always can say to yourself, oh, I can solve for y and it's 1/16 x squared, and that's a pretty flat parabola. Y equals 1/16. You always think that in your mind as a check. So for us, if p is 4, and we know the vertex is 0, 0, and we know the vertex is 0, 0 because it's not x minus something squared and y minus something. So it's not shifted. So vertex is here. P is 4. That means we need to go up 4 to get to the focus. So the focus, 1, 2, 3, 4 is right there. That's the focus. And it means that we need to go down 4 to get to the directrix. because P is positive, I know it's going to open up, not down. And the directrix is a line. So you're going to be asked on the test to find the equation of the directrix. So it's not D equals something, but I'll put D in a colon, and we'll say the directrix is y equals negative 4. That's the equation of a line, y equals negative 4, equation of a horizontal line. The focus will have coordinates. It's a point. And that's going to be at 0, 4. And the directrix and the focus are always split. The vertex splits it right in the middle. All right? And then we just draw the graph. And now we know from past experience that if we divide it by 16, then it's super flat. And we're not trying to get super precise here. We know that it's a parabola. We know it's going to be flat, and it's going to look roughly like that. You can try to draw it precisely by trying to find points so that this distance and this distance are the same. You know, that's the idea. So as you're trying to draw it, you're sort of thinking in your mind as you draw it, you want to try to maintain that common distance. Okay, so for this one, over here, this one is going to open horizontally because the y is squared and the x is linear. So it's like x equals y squared is a horizontal parabola. P is negative though, so it's going to open left and not right. So if we have a vertical situation, P positive up, P negative down. Horizontal situation, P positive right, P negative left. P is negative 1/2. We know the vertex is 0, 0. There's a shift up there. So the vertex is 0, 0. And then P being negative 1/2, that means that we're going to go over to negative 1/2 comma 0 for the focus, and over to positive 1/2 for the directrix. The focus will be there, and the directrix will be there. The coordinates of the focus is a point, so we'll have an ordered pair. The directrix is a line, so it should have an equation. So the directrix will be the vertical line, x equals 1/2. The focus will be the ordered pair, negative 1/2 comma 0. Now again, our previous experience with parabolas, if we divided by negative 2, we'd have x equals negative 1/2 y squared. And we know if half is the coefficient, it kind of flattens it. So we know that, and you should use that to your advantage. But again, be thinking as you graph it, you want to be picking points on the parabola in a way that those two are equidistant. I didn't do a great job there. Let me try graphing it again. So graphing it just a little bit steeper. Because it should be the case that if that point right there is on the parabola, that vertical distance and that distance to the focus should be about the same. It should match, more or less. Okay. So, again, the weird thing is that you're isolating squares. So here we're going to isolate y squared. So different than what you've done in the past. Here we're going to isolate x squared. In both cases, you set 4p equal to the coefficient. We always are going to equate 4p equal to 2, or equal to whatever the coefficient of your linear term is. The p in that case would be 1/2. All right. Both have a vertex of the origin. Both of those vertex of the origin. There's no shifting. We'll get to the shifting business very soon. Okay. And before we go on, let's identify. Is this a vertical parabola or a horizontal parabola? This is horizontal because y is squared. Or if you think old school, like we used to think, this is x equals y squared, so we're doing this kind of thing, as opposed to y equals 1/2 x squared. So however you remember it, there's several ways. The important thing is that this is horizontal. So this is going to open right or left, but because p is negative, which direction will it open? Yeah, it's going to open left. This one, p is positive, so it's going to open up. So we know that kind of from looking at p. We have to be able to identify from that standard equation, once we've isolated the square, whether it opens vertically, and then more precisely whether it's up or down, whether it opens horizontally, and then more precisely whether it's left or right. And it's all based on the sign of p. Okay, so this one's opening to the left, and we know that the vertex is at the origin, so something like that. P is -1. So that tells us that the distance to the focus is 1, and the distance to the directrix is 1. So the focus is right in there, the directrix is there, so this thing needs to be sort of equidistant, so it's kind of like that. I'm just kind of thinking in my head, all right, that distance and that distance must be that same. So the coordinates of the foci, of the focus, there's only one. The focus is -1 from 0. And the equation of the directrix of the vertical line, x equals to 1. For this one, we've already identified that it opens up and the vertex is the origin, so that should be sufficient. Let's see, p is 1/2. So that tells us 1/2. There's the focus right there at 1/2. The vertex is there, and the directrix is down here at -1. Coordinates of the focus, 0, 1/2. Equation of the directrix, y equals -1. And then that parabola is going to be sort of like that. In our minds, we're sort of thinking as points, that distance should be about the same. Not quite, but close enough. So those ones are the ones that are at the origin. Those are ones that you should have done before in 121. And the stuff that should be new is shifting them away from the origin, if you took 121 here. So let's try to deal. Oh, here are some others that are centered at the origin. Let's deal with these first, I guess. Okay, so let's find the equation given this information. Draw a picture. Picture really, really helps. So we have that our vertex is at the origin. We have the focus is up at 0, 10. So the focus is up here at 10. So where's the directrix? -10. The directrix would be down here. It's the line y equals -10. And if we drew a picture of this parabola, it's going to be kind of flat, sort of like that. So that we're kind of thinking of that distance and that distance as being the same. It should be a little flatter. Maybe I'll try to flatten it out a little bit more. So that looks a little bit better. So that distance and then that distance is the same. Okay. So let's piece it together. It's opening vertically, so we know p is positive. We also know that x is going to be squared. Right? So the standard form would be x squared equals 4p times y. Now we know what p is. What's p? P is 10. P is this distance right here. So p is 10. So x squared equals 4 times 10 times y. So x squared equals 4y. That would be our standard conic form for that parabola. Yeah, so it should be very flat. Y equals 1/40th x squared. Let's try this one. Picture. Okay, so here they tell us that the directrix is at √2. That's x equals √2. That's the vertical line for the directrix. And the focus is equally away from the x-axis at -√2, 0. So obviously the vertex has to be at the origin. It's got to be dead center. This also tells us that p is equal to what? Positive √2 or negative √2? Negative √2, because it does open to the left. It's opening left, so that means that p is negative. If it opens down or left, p will be negative. If it opens up or right, p is positive. So p will be negative. Parabola is something like that. So if it's opening sideways and the vertex is at the origin, the standard form that we're looking at is y squared equals 4px. Well, we found p. P is negative √2. So our equation would be negative 4 √2 times x. That would be our standard form. Standard conic form. One more of those guys. Again, picture. Really, really helps. So y equals negative √3 is the directrix. Down there. Y equals negative 3. And then the focus is at -2, positive 3. Let me move this line a little bit. So -2, positive 3. Here's our focus. So where does the vertex have to be here? Yeah, -2, 0. So here's going to be our first one, not centered at the origin. So there is our vertex. So the vertex is -2, 0. And this one is opening up. The focus is always inside the parabola. So it's opening up, like that. And we know that p is what? Positive 3. All right, so let's see if we can use our ingenuity. If this was at the origin, we know that it would have what as its standard form? Yes, so this would be if it was at the origin. 4by, sorry, thank you. 4by. Now, if the center is hk, we're going to do just what we did with ellipses and hyperbolas. It's going to be x minus h and y minus k. So all we're going to do is make this x minus h squared equals 4p times y minus k. That will take care of shifting h units horizontally and k units vertically. Let's see if we can piece this together then. So x minus h, and when we have the vertex, h is the first coordinate, k is the second. So what does this become? X plus 2, x plus 2 squared equals 4 times p, so that's 12, and then y minus 0, and that's it. So that's the standard equation for this parabola, standard conic equation. Alright, so let's get to some others. Unless somebody has a question on it. Anybody have a question on, yeah, on that? Yeah. Okay. So here's the summary of the shifted ones. So instead of x squared equals 4py, it's exactly what we just read. Instead of x, we have x minus h. Instead of y, we have y minus k. Similarly, instead of y squared equals 4px, we have y minus k squared, and 4p x minus h. Not too complicated. If you get the origin graphing, the shifted ones, not too crazy, but definitely going to take us a little work here. So the first one is already in the standard form for us. What do we see the vertex as? Close? Negative 2, 3. So that's a common mistake. We really have to just sort of get into the habit of remembering that the first coordinate's associated with x, the second coordinate's associated with y. So that's the x coordinate of the vertex, that's the y coordinate. And it's opposite of what we see. So there's the vertex. Then we set 4p equal to negative 20, giving p equals negative 5. And we have to decide. Does it open down or left? If p is negative, it's going to open down or left. So opening left, everybody agree? So it's kind of like x equals y squared, so we know it's horizontal. Okay, so it's going to open left. Okay, so that tells us then that we're in this situation. So negative 2, 3, opening left. Negative 2, 3, there's the vertex. P is negative 5, so that tells us our distance that we have to travel to get to the focus or the directrix is 5. So from there, we have to go left 5. 1, 2, 3, 4, 5. The focus will be right there. And the directrix, we have to go 5 the other way. There's 2, 3, 4, 5. The directrix is a line. Just sort of like that. Didn't really ask us to graph it, but we can. I'm just going to sketch something like that. It's opening to the left. The focus is inside the arch. All right, what it did ask us for. Coordinates of the focus. What would the coordinates of the focus be? So, what was that, negative 8? Negative 8, 3? That's right. No. Negative 7. Negative 7. We're going to go 5 units to the left of negative 2. So negative 2 and then 5 more, so negative 7. And then the y value, of course, is 3. And then the equation for the directrix, x equals 3, the vertical line. So it should be x equals a constant. All right, I'll do one more here, and then I'll give you the brains. Okay, so this one up here. Obviously, we have to complete the square because y is showing up in 2 different places. So we have to complete the square. What are we going to add to complete the square in y? 9. Divide by 2 is 3 squared, it's 9. So I'm going to add 9 to both sides. Keeping the squared variable on the left, the unsquared variable to the right. So I've added x and I've subtracted 16 and then added 9 to both sides. So this will give us our standard conic form. That's going to be x minus 7. Now I'm going to do something with parentheses here just because Hopefully that's a little clearer. I want it to be pretty obvious that the coefficient of the linear quantity is 1. So 4p is going to be 1 here. So 4p is equal to 1. So p will be equal to 1/4. Okay? So that's a positive p-value. That corresponds to up or right. And because y is squared and x is not squared, it's going to open horizontally, so we're going to conclude that it opens to the right. And what is the vertex? 7, -3. We go to the x group to figure out the x value of the vertex. We go to the y group to figure out the y value of the vertex. Now we draw a picture. And maybe we don't have to get super precise here, but we know that that's the vertex and we know it's opening right. So even just that is going to be very helpful in terms of figuring out what comes next. So we know the focus has to be on the inside, and we know the directrix has to be on the outside. So we're dealing with something like that. And P is only 1/4. That's why I want to just not try to get too precise, because 1/4 is super hard to draw if we're out there at 7 -3. But a rough sketch like this should be enough for us to conclude that the coordinates of the focus are, let's see, the y value of the focus first, that's the easy one. The y value of the focus should be the same as the y value for the vertex, -3. And what should the x value of the focus be? Yeah. So the x value for the vertex is 7. The p value is 1/4, so we have to go from 7 over 1/4, so 7 1/4, which they would write as 29/4 usually. And then the directrix, vertical line, so it should be x equals something. We have to come 1/4 unit to the left of the vertex. So the vertex is at x equals 7 1/4 units, so 6 3/4. 6 3/4, so 27/4. Should be that vertical line. Okay. You guys try 30. This is going to be exciting. Okay, Josh. Yes, complete square. Yep. Or if you want to be kind of sneaky about it, you can break the 10 apart. Write the 10 as 9 plus 1. And use the 9 as the square. couple of ways. So the typical procedure here would be to leave the squares, leave the x's on one side and put that 10 on the other. That would be kind of it. If somebody had to tell you a procedure, this would probably be the most easy to describe. And then complete the square nails. I think I heard a couple of you say add 9 to both sides. You should get to this. Who knows what P is going to be? So I'm going to reorder this just so that it's in the same position as the equation. And again, we have a coefficient in front of the linear side of 1, so P will be 1/4 again. P 1/4. Which way does it open? Up. So the x's are squared, the y's are not, which is vertical. And because P is positive, it opens up. What's the vertex? -3, 1. So when we draw our sketch, just to orient ourselves, and you don't have to get super precise with this sketch, but just enough. You know it's opening up. Just so you know whether you should be adding or subtracting, and whether it should be adding or subtracting from x or from y. Just helps. So your focus will be in there, and your directrix is going to be down there. If you just get a general sketch like that, it will help you to do your arithmetic. So the focus, is it obvious that the x coordinate of the focus is -3? It's kind of lined up vertically with the vertex. So that's going to be -3. And then here's the tricky piece. So P is 1/4, 1/4. So we have to go up from the vertex 1/4. So that's going to put us at 1 plus 1/4. So that's 5/4. Our focus. The directrix is a horizontal line, so it should be y equals something. So we're going to go down 1/4 from 1. So 3/4. All right, try 32. so we have to add to both sides. What was that? 1/4? Because that coefficient of y is 1, so we have to divide it by 2 and get a 1/2, and then we square that and get a 1/4. So that number that we have to add to both sides is a 4. And then you can factor it. Have you guys started to notice that when you complete the square, it's always following this pattern? That coefficient divided by 2 is always that number there when you complete the square? When you divide the coefficient here of 1 by 2, you get a 1/2. That's always what that number is going to be. Every single time. What? -17/4. All right, so what is the vertex?
-4,
-17/4. -1. You'd rather use mixed numbers? Decimals? Don't use decimals. You can use fractions or mixed numbers. Don't use decimals. Use decimal, you never know what the heck's going on. You never know if it's rounded or unrounded. Or yeah, don't use decimals. Do you prefer decimals? 17/4 is pretty reasonable, isn't it? Not that good. I mean, the problem with decimals is if you have a repeating decimal, then it gets all messy. Yeah, in this case, it's not. That's the way usually fraction. All right. So then, what is p? So we have the same kind of weird situation, which is it's the most common one to make a mistake on. So that's why I've seen it much. But 4p is 1. So p is 1/4. Okay. So let's go ahead and graph it. So negative for now I'm talking 3. But again, we don't have to get super precise here. It's more of the orientation of what's where. Okay, p is positive 1/4. And I put that little arrow there. That arrow is just telling me to solve for p. That's not supposed to indicate the direction. What direction should this thing open? It should open where? To the right, even though I didn't mean that arrow to indicate that it's opening right. But it is going to open right. Because p is positive and the y's are squared and the x's are not. So opening right, let's just draw that so we have a sense of where the focus is going to live and where the directrix is going to live. So that sketch should enable us to get the coordinates in the equation for what we're looking for. So the focus then has the same y coordinate as the vertex. So what's the x coordinate? -4. We're going to take that 1/4 and we're moving to the right 1/4 So we're going to add 1/4 to that, so that's negative 16/4, which is negative 4. The directrix, so vertical line, that's going to be 1/4 to the left of that x-coordinate, so that's going to be at negative 18/4, which is negative 9/2. Any questions on any of the steps? All right. So an application. Let's do an application. Okay, so here we have a flashlight, a heavy-duty flashlight, not just a flashlight. Parabolic cross-section with a diameter of 6 inches and a depth of 1 inch. So if you pull off this lens piece, it's 1 inch deep, 6 inches across there. And the first question, well, first it says, put a coordinate system on there, blah, blah, blah. But our question is, how far from the vertex should the bowl be if it's to be placed at the focus? We want to figure out how far the bulb should be from this parabolic lens that's going to reflect the light. All right. Part A simply says put in a coordinate system. So we're going to put in a coordinate system. Like that. The vertex is at the origin. So what should our standard form be for this parabola? So which variable should be squared? Y. So y squared equals 4px. That'll be our standard form. So we have to somehow find p. We need to find p, because p is the distance we're looking for. That is the distance from the vertex to the focus. Do we know a point? So this thing is a parabola. Let's see. We've got this graph right there. Do we know a point on that graph? If we knew an ordered pair on the graph, we could plug in that ordered pair and then isolate p. So 1 moves us over here, and that point right there would be 1, 3. Similarly, this point down here would be 1, -3. So if we take one of those points and plug it in, so if we plug in -3 or 3 for y, we get 9 equals 4p times x, which is 1. So that tells us that p is equal to 9/4. So how far from the vertex should the bowl be positioned if it's to be positioned at the focus? 9/4 inches. All right. So we didn't finish off though. And also, part A also asked us to actually write the final form of the equation. So once we have p is equal to 9/4, we can plug it back in, and our final equation would be y squared equals 9x. That'll be our final equation. So once we've solved for p, we're just going to plug it back in. So we can get the standard conic form of this parabola. All right. Similar one, except they don't draw a picture for us. So spotlight has a parabolic cross section. It's 4 feet wide at the opening, 1.5 feet deep at the vertex. How far from the vertex is the focus? Same idea. Draw a coordinate system. Let's open it the same direction so that we can use what we just did a minute ago. Oops. Take that. All right, so we have something like that. And they tell us that it's 1.5 feet deep at the vertex, 4 feet wide. So if it's 4 feet wide, this point right here is up at 2. It's 1.5 feet deep, so this is 1.5, which let's write it as 3/2, 2. So that's on the parabola. Again, it's opening to the right, so it's going to have it's going to be just like the other one. So which variable is squared? So y squared equals 4px. We know that point is on the parabola, so we substitute in the coordinates. So we have 4 equals 4p times x, which is 3/2. So we solve that for p, and we get p is equal to 2/3. So our conclusion is 2/3 of a foot. That's where the focus will be. The focus will end up being right there. All right. Let's see. So that was the last one from that. Yeah, let's start the. So our last section is the nonlinear systems. Now that you know conics, you can solve nonlinear systems. Conics are nonlinear equations. So now we can solve more complicated systems. So with linear systems, you could use substitution or elimination. Those were two techniques. Sometimes one worked better than the other, but usually it didn't really matter. One was just barely harder than the other, barely a little bit more work. It didn't really matter. With nonlinear systems, almost always, 90% of the time, with nonlinear systems, substitution is going to be better. Most of the time. This one, the answers aren't nice, so the instructions said just to graph it. And what we want to be able to do now is identify where the intersection points are. And algebraically, sometimes you can solve them, sometimes they're really complicated. We'll take a look at that in a second. But we know that this top one here is an ellipse, and we could graph that. We know the bottom one is a line. So we see that there are, in fact, two solutions to this system. There and there. And the instructions said just to graph. I don't know why they said that, but we'll probably find out in 1 second. So if we wanted to use elimination here, we could solve this bottom equation for x, and we could plug it into the top equation. From the picture, it looks like that coordinate at least is nice. We'll find out. If it gets too messy, we'll just plug it with decimals. So 16x squared plus 9y squared equals 144. Let's see if we can solve for y. Okay, let's do some distribution over here to get this all cleaned out. 80 plus 48, that's 128. All right. Finally, we're getting to some like terms here. So 25y squared plus 28y plus 112 Okay, now I know why. So just grab it. We have that. Now looking at the graph, at least I would suspect that y equals -4 is the solution. Looks promising, doesn't it? So let's just do a little synthetic division quickly. If -4 is going to be a 0 of this, how would I do synthetic division to factor that thing? -4 in the corner, -4 is the 0, then we would do 25, 128, 112. Determined to check this out and see what's happening. So that's -100. And then that's 28 times 4, 56 times 2, which is -112. Right. So this tells us that -4 is definitely 0. So that means that y plus 4 is a factor. Correct? So we could factor this into y plus 4 and 25y plus 28 equals 0. So this tells us that our two y values are -4 and y equals -28 25ths. Okay. So how do we find the x's? What do we always do in the system once we have one coordinate? Back substitute. And so here's something that's going to be really important with nonlinear systems that's different from linear systems. With linear systems, did it matter which equation you plugged your y's back into to get your x's? No, it didn't matter. For nonlinear systems, it matters. And the rule of thumb is to back substitute into the equation that gives you less answers. Like if I take this y value of -4 and I plug it in right here, y value of -4, I get an x value of 0. But if I take that y value of -4 and I plug it in up here, I'll get some stuff. I subtract it, I divide by 16. How many x's am I going to get? Possibly 2. Very possible 2. So when you're back substituting into a nonlinear system, you always want to substitute into the easier equation. The equation that's going to give you less options. Because you could get an extraneous solution if you plug back into the wrong equation. Okay, so what do we have here? So it's x is equal to y plus 4. Okay, so we get 0, 4. Nice. 0, -4. And then over here, if we plug that in over here, we get -28 over 25 plus 100 over 25. So we get 72 over 25. Comma -20 over 25. Okay, so those are the two solutions. Those are the two ordered pairs where they intersect. So we'll stop there. We did one of them. We'll finish up this section on Thursday. Do a review on Tuesday. Take a test on Thursday. Go snowboarding on Friday. And live happily ever after.